Excited to be here. I used to be a student here, I guess, many years ago, or not many years ago, depending on who you ask. But I'm very excited to be here again. And what I'll talk to you about today is another market design problem. And it's about matching. It's not because it's two-sided matching. It's because it's important who goes where. And some inspirations for the problem is Chicago public housing. It's let's say a leading example. And let me tell you a few things about how applicants for public housing get assigned apartments. First, there's a waiting list. And the waiting list is very long. It has approximately 60,000 applicants on it. And it doesn't have 60,000 applicants because the 60,001 didn't want to join. It's because the 61,001 was not allowed to join. The waiting list is capped at 60,000 people. Basically, think of it as infinite demand. For a pretty limited supply of public housing, Chicago public housing has about 20,000 apartments less that allocate to the applicants. Those turn once every 5 years, which means that if you're at the end of this list, you're unlikely to get an apartment ever. You're more likely to drop out of the list without getting an apartment. So one can think, okay, why are we thinking about this assignment problem? It's clear that all the apartments can be assigned. So what is there to think about? So here's this crude map on the left side illustrating where the apartments are. And it's a bit hard to tell from the scale, but the south side of Chicago is about an hour or more from the north side of Chicago. And at least geographically, those are very different apartments. If you live up next to Evanston and you're given an apartment in the south side of Chicago, you have to move across town. You have to take your kids to a different high school. Maybe you'll have to commute for an hour of work. While some applicant who actually lives in this neighborhood will find this apartment great. So it wouldn't make sense to randomly assign those apartments. And we really want people to choose the apartments that are right for them. Different apartments will be right for different people. And there's still, so there's a challenge here in the assignment. This challenge is actually not trivial, given that apartments are not assigned all at once, but they get assigned over time. So, yeah.
Are people allowed to trade apartments once they have them?
So there's some procedure that allows you to request a transfer, but you can think of even getting an apartment that you don't want, spending 2 years in it and trading eventually as a welfare loss as well. So in the paper I won't allow people to trade, and you can think of the welfare loss from getting a mismatched item to be the welfare loss given that you can still trade it eventually. So here's a very stylized simple example just to explain that when items arrive over time, you have another challenge to get an efficient assignment. And this is because people are impatient. They have a preference over when they get the item first, even though socially waiting cost will balance out. So think of just two agents, A1 and A2. They both have to wait. They both have a waiting cost of C per period. So everybody wants to get assigned first. And they have different preferences. One wants a southern apartment, one wants a northern apartment. And the southern apartment arrives in period 1, the northern apartment arrives in period 2. So the allocation that will be socially optimal will be that the agent who prefers the northern apartment will get it in the first round, and the agent who prefers the southern apartment will get it in round 2. But the opposite assignment, where both agents are mismatched, gives less waiting cost to agent 1. And if you ask agent 1 personally, you may prefer to take the southern apartment, although it will cause both agents to mismatch because it saves him on the waiting cost. So just letting agents choose, it does not necessitate that we will get the socially efficient outcome. And this is actually a practical concern, because if I have a southern apartment in Chicago, and I go to applicant number 30,000 and I ask him, do you want this apartment? He'll say yes, regardless of whether it's a good apartment for him or not. And this assignment for waiting list is quite a common phenomenon. You see this in public housing, in organ donations that you heard a lot about, but also in nursing homes that are private nursing homes. Often they have waiting lists for admission rather than just increase the price. Even NFL sports team for season subscription, all waiting list to sign items rather than just increase the price. And you want to ask what is the allocation properties of this waiting list, given that you allocate things dynamically over time. And you are concerned that people may not be choosing the best thing for them because they're impatient. And in a way, that's a problem just because of the incentives of the situation, not because that agents arrive over time. It's not that at the time where the southern apartment came, there's no applicant on the waiting list that would like a southern apartment. There may very well be one, but I don't know if it's number 31,000 or 30,000. And I know that if I ask any one of them, they will just take it, because all of them have an incentive to take whatever I give them, because they're expecting a very long wait. So here I have a mechanism design problem that says, given this dynamic nature of arrivals, how can I ask people and offer choices in a way that actually will reveal the preferences of people and allow me to find out who is the matching agent inside this large pool of potential agents that I have. So what I'll do to address this is that I'll start from a very stylized, simple model that helps us think about the matching in waiting list issue. So I'll have two types of agents, two kinds of items, and different types of agents will prefer different kinds of items, and welfare will depend on whether I am able to match agents to the items they like more. Then, given this model, I'll start by analyzing just a benchmark policy, the policy that the first policy that would probably come to your mind is a sensible one, which is to hold a waiting list, offer people according to the order in line, and if you don't want an apartment, you should be allowed to decline it, and we should offer it to somebody else, and you can keep your place in line. And we'll start by analyzing this kind of mechanism. We'll find that it's actually pretty tractable to analyze it, as we can think about it as a buffer queue mechanism, and I'll explain what is that in a couple of slides. And given the tools that we develop here, we actually will get also tools to generalize this mechanism and ask the mechanism design question. Can we redesign the policy of the waiting list to get more welfare, to incentivize people to match better with the more preferred items? And then we'll derive an optimal policy, which will have a new queuing policy in it. And this policy will be an optimal solution in a mathematical sense, but you'll see that it has some issues that will prevent it from being some plausible suggestion to a practical mechanism, and therefore we'll move to the last part to try to limit the scope of mechanisms that we want to look at to simpler mechanism that will be more robust, and we'll find a simpler policy that is not optimal in the same sense, but generates in a way pretty good welfare as well, and has much better properties. It's much more robust, much less dependent on parameters, and safer for participants. And maybe I'll get to talk about something else, but probably not. Okay, so let me jump in and explain the model, which is very stylized, very simple. Think of the waiting list as being infinite. So in the back of the head, like the waiting list is not literally infinite. People come to the waiting list over time, and they get assigned and leave. It's a dynamic process. But I don't really care when somebody arrived on the waiting list, as long as when I call on him, he was already there. And given that there are 60,000 people on the waiting list in Chicago public housing, there's 100,000 people waiting for kidneys, and various other big numbers for other systems, then we can just think of the pool of agents is infinite, meaning if I ever go ask agent number 30,000 on the waiting list, he already arrived by the time I want to ask him. So what happens when I ask number 13,000? I don't know its type. People join through some random process, and they don't reveal anything to me at the time of joining. So before I ask them, there's some probability that they're going to be of type alpha, and there's some probability that they're going to be of type beta. Alpha types like item A, beta types like item B. They get a value of 1, normalized to 1 from getting their preferred item, and they get some value V, which is lower than 1, from getting their mismatched item. But every period that they stay on the waiting list costs them C. Think of C as paying rental while you're on the paying rent while you're waiting for a public housing apartment, or going on dialysis while you're waiting for a kidney.
Are people arriving? Are the agents, are they arriving, or are they all there at the beginning of the story?
So as far as the model concerned, I can think of them as being there. Implicitly, I need for that two things. First, that the waiting list is overloaded. There's so many people. And second, that waiting costs are sunk. That if you waited for 10 years on the waiting list, your stay today is just the same as if you just joined.
Any particular reason why you do additive cost rather than discount factor?
Mathematically, it's easier to deal with, and I think it generates the same insights. And items will arrive dynamically. Items are the short side here, the most scarce side. So an item will arrive once every period. The kind of the item will be randomly drawn. It's either an A or B. Think of every month one apartment gets released. And it's either a southern or northern apartment. And the item will be assigned in the same period in which it arrives. This is a restriction on the mechanism, which may be not restrictive in many cases. Like kidneys have to be assigned when the kidney arrives. You can say that I don't want my apartments to stay vacant. And the probability that an A apartment will arrive in a given period is denoted by PA. The complement probability is that it's a B apartment. And for the sake of the talk, I'm going to assume that the proportion of agents who want an A apartment, P alpha, is equal to the proportion of A apartments that will arrive. So that means that if I had all the apartments and the agents in one period, everybody will just choose their preferred apartment. We'll have no mismatch. Every alpha agent will take an A apartment and every beta agent will take a B apartment. Every mismatch in the system will be because somebody had incentives to mismatch. Yes.
You say you're assuming that items must be assigned in the period they arrive, but that would follow from efficiency anyway. It would be inefficient. Since both types get positive utility from getting the apartments, an efficient mechanism should presumably assign it.
I think this is true, but that requires a proof. That's like there's some slight things.
You might want to introduce some queuing
Yeah.
as a screening device, but apart from that.
Yeah. So given this model, the next step is to say what are the outcomes that I want to implement, and because all agents have the same waiting cost, we actually have a very simple criteria for welfare. So think of welfare as maximizing the total utility generated by the stream of items that we have. So we have a bunch of agents that will be assigned. We want to maximize the value of assignments. Think of it as we have an apartments in the south and in the north. We want to generate the most social value from those assignments. Every time we mismatch an apartment, we get less assignment value. And every time we assign an apartment in any way, we save waiting costs. Now some applicant doesn't need to pay rent. But it turns out that we actually don't need to think about the waiting cost when we think about welfare, because in aggregate, total waiting costs are going to be constant. Just think of the system, think of the waiting list as having a large fixed number of agents on it at any point in time. At any stage, at any period when an item arrives, one of them will get assigned. Because we said an apartment will be assigned every period in which it arrives. So the agent which will get the apartment will stop waiting. That saves us on waiting cost. That generates some welfare. But how much welfare we generate does not depend on which agent we assigned it to. In any case, we assign it to one agent who will stop waiting, and the rest of the agents will have to keep on waiting. The mismatch value, though, does depend on who we assign it to. If we assign it to somebody in the north versus the south, they have the same waiting cost, but in one case we generate higher welfare. So, personally, privately, agents will care about their private waiting cost, but globally, waiting costs cancel out, saying when I wait more for an apartment, somebody else must wait less. I never sort of generate more wait, I just let other people pass me in line. So, and this is sort of the major source of tension in this model, that the system just cares about matching agents to apartments, agents care about the waiting time. So from now on, our goal is to generate mechanisms that will minimize mismatch. And just remember that this is synonymous to maximizing welfare in this model.
You don't have another constraint that you want to violate the order as little as possible. So you don't want to jump.
I'll get back to that. This is something I assume does not constrain me.
It's not an issue.
And I don't have a slide on this, but I'll be happy to discuss this later in the talk. Yeah? So let me skip the literature review and come to the first not very sensical mechanism. If I don't ask agents for their type, what is going to be the welfare under the system? Well, we said waiting costs cancel out, so I just need to know what is the probability that I mismatch an apartment, that an alpha agent takes a B or a beta agent takes an A. And the probability, if I just randomly assign, is the probability that an A item arrived in a period when I asked a beta agent, or that the B item arrived in a period where the next agent I asked was an alpha. And if those probabilities are all P, I get 2P 1 minus P, which is a half if P is a half. Basically, I mismatch half of the apartments. This is clearly not a good system. We want to do better. Yes? That would be the value of assignment, which I'm assuming that once you're assigned, you're out of the mechanism. I just attribute you the value and ignore all the rest. Yeah.
I'm thinking that they are going to stay that house very long.
Mm-hmm.
Then there's a huge cost of reporting the purchase.
So they get to choose, right? And I'm trying to figure out what is the welfare maximizing way to let them choose. Now, I have a very simple sort of model where the choice is just between preferring A and preferring B, not about whether I have a strong preference for each one of them. That's is a clear thing that this model is missing, and add to the realism. But what are the things that I'm concerned about as a designer are, first, what they can choose, second, what I know about them. And here there's an assumption that whether they waited a short time or a long time, I don't know anything more about their preferences. In expectation, if you prefer an A apartment, this is your expected utility. If you prefer a B, how long are you going to stay there? If I can solicit this, I'm just going to take the expected value. Yeah?
You're ruling out transfers.
Yes, and sorry, I wasn't explicit on this, but yes, there are no transfers in this model.
And you can't correct the mismatch.
So there's still going to be some welfare losses, even if eventually a mismatch will be corrected.
Right.
So I'm sort of saying...
The probability should multiply by the number of times before a mismatch is corrected.
So think of this as going into this V.
Yeah,
If The V is the value of being mismatched.
Per unit of time.
No, it's not per, it's realized once. This V is once I mismatch, I just like give you a value of V from like the future value that you get. No?
No.
Once you match, you're out of the system.
That's what I mean. You don't correct it. You could think of a system which you're on it, but you have some.
Yeah, I could endogenize those values as well and think of a system where I think, yeah, yeah. No? Yes?
There's no new people entering the waiting.
So I don't differentiate between new people and old people because I don't really care here when did you arrive.
Well, you say that the waiting cost comes about, but if there were new people entering the list,
Yeah.
in the case of
So it may be that at period 1 there are n people, at period 2 there are m people, but by assignment I can always reduce whatever the number of people is in a period by 1. So it actually doesn't depend on much. I just need some finiteness to make the utilities be finite, but other than that it works. Yes? Sorry? What? So this is like public housing is just an example here. Like think of it as a general allocation of waiting lists, but generally it's low income people. Okay. Okay, so just randomly assigning people does not create good welfare. A lot of people will be mismatched. So here's just a brief formalization of like this policy that I told you I'll start as analyzing as a benchmark. So what happens if we have a first come, first serve waiting list where I allow people to express their choices by declining items. So one way to do this was to say there are 2 waiting lists, one for A, one for B. When you join, decide which one to join. That would mean that you have to choose whether you want an A or B well ahead of time, because you join a waiting list, you join a different waiting list, and then you wait for maybe 2 years before you get assigned. Here I ask you just at the end. You join the waiting list. I don't solicit anything about your type when you join. I just ask you when I have an apartment at hand, I offer you, this is an apartment, it's a B. Do you want a B? If not, you can express your choice for an A by declining it, letting somebody else pass you in line. I can offer this apartment for somebody else. And then I have to compensate you in some way for being, in a way, benevolent. When you decline an item, you allow somebody else to take this apartment instead of you. You say, I'm willing to wait longer. So I should try to make you as well off as I can for doing this deed that is actually good for the social welfare of this system. And what I do here is I let you keep your place in line. This seems like a pretty sensible thing to do. Right? No? So let's analyze this mechanism. What happens if I do this process where I continuously offer to people and they have the option of declining and keeping the place in line. So suppose you're the alpha that is first in line. So the first agent, if I offer you an A, there's no question. It's your most favorite item, and you don't have to wait any longer if you take it, so you take it. But if you offer the B, then you actually have a choice. If you take the B now, you get a value of V, a mismatch value. If you decline it, then you can show that since the problem is stationary, you'll decline all future B's as well. And that would mean that I decide to take some extra weight now, let some other people pass me in line, and I'll take some extra weight until an A will arrive. So my eventual value that I get from assignment will be 1, but I have a cost of waiting, which is the extra weight that I'm going to have. So I have a cost of C per period, and the expected time until an A will arrive is 1 over P, because the probability that an A will arrive in every given period is P. So assuming that this expression is bigger than this one, the first agent will decline the mismatch. And then we can go on and offer the item, the B item, to the second agent in line. Now, the issue is that the second agent in line does not face the same trade-off as well. If I'm the kth agent in line, and I just got offered a B, it must be that all the agents in front of me decline this as well. Which means that by this, I know that there's a bunch of people in front of me that are waiting for an A. So if I'm the third agent in the waiting list and I got offered a B, 1 and 2 are waiting for an A, they'll get an A before me. So now my value for getting a B is still V. It's the same value. But my value for getting an A, waiting for an A, is now not the expected wait until the first A will arrive. It's the expected wait until the kth A will arrive. So my waiting time is K over P. And this means that sometimes I would prefer to take the B rather than wait for an A, because if K is large enough, if there's enough people ahead of me that are waiting for an A, the waiting time for an A becomes very long. At some point, it's not worth for me to wait. I'd prefer to just take the mismatch. Yes?
Is the information within, but does the man in the 10th place, does he know that the people before him are waiting?
So I assume that you know your place in the waiting list.
Okay.
Yeah? Otherwise, I'll have to take some expectations here over beliefs. And given that I tell you that you're the 10th person on the waiting list, given that, you already know that and everybody ahead of you declined the item that you were offered, and therefore must be waiting for an A. Huh? And so, two things. One is we can think of a max. We can think. Okay, let me do the first one. One thing is we can think of me declining a B as sort of going on another list. I say I'm waiting to wait longer for an A. Figuratively, I can think of this as joining a new queue for A. I can go immediately now to take a B, or be the kth person on this line of people that will get the next A's that will come. And I'll call this buffer queue in a second. And this actually helps us analyze the dynamic process here. Second, there's only a finite number of agents that will be willing to decline a B that can accumulate together, because there's a maximal position, which I denote by K alpha. If you're in a position above K alpha, the wait for an A is too long for you, and you prefer to just mismatch. Yes? Sorry, yes?
I can see the advantages of this method, but from the point of view of the designer, the way you define it makes sense just to have two separate queues for A and B. Then you don't get any mismatches. Anyway, you said that waiting time
So-
passes between.
So if you have two waiting lists, you have exactly the same phenomena happening, because different people will join the waiting lists at different times. And when I come, I may see that the waiting list for B is longer than the waiting list for A. And then I'll have a maximal K, which is what is the maximal gap that I'm willing to tolerate. So the waiting list for B is longer by 12 people. Yeah? The individual will sometimes, at some point where the difference becomes big enough, they'll just go to the shortest line.
So you will get mismatches that the designer does not know about.
Yeah, here as well. Once I know that K alpha agents decline the B and I offer it to the next one, I know he's going to take it. And at this point, I don't solicit any information about his type in this mechanism, because I know that both types will take the item. Yeah, so
This just follows up the question a moment ago. The mechanism designer can presumably choose how much information about the waiting list to reveal, and so it might, depending on the parameters, it might be in his advantage not to reveal how long the waiting list is, so that everyone is operating on the expected queue, which might be small enough so that they're willing to choose the right match.
So two answers to that. One is in public housing, you may see it as a constraint that you have to be transparent and give agents the information. Second, I'll show you in a bit that an optimal mechanism can actually do as well as a mechanism that withholds information, as well as a mechanism that withholds information.
So,
Yeah.
so you can, even with revealing information, you can still.
I can still
You could
achieve
still-
this
okay.
the same optimal level. Huh? So again, this is just an analysis for this simple first come first served queue with declines. Huh? So, so again, for this mechanism, just to illustrate it graphically, here are the waiting times for each positions. If let's say p is equal to a half, if I'm the first in line and I decline, I wait 2 units of time. If I'm second, I have to wait 4 units of time till the second item will arrive, third item, fourth item, and so on. And there's some threshold. There's some W bar. There's 1 minus V over C, which 1 minus V is the benefit that I get from getting my preferred rather than mismatched item. Divide by C to translate it to how many periods I'm willing to wait. And that gives me a threshold of which position I'm willing to take. Here, the third position is the last acceptable position. The fourth has a waiting time that is above my benefit from getting my preferred item. So, given this choice of agents, we mapped the individual choice, but we want to know what is the system dynamics. How often will it happen that I accumulate k alpha agents and then try to offer to the next one and get a mismatch? So to that I need to understand what is the entire dynamics, which is not every agent here will only make one choice, but the choice of every agent depends on what happened before him. And the dynamics is actually very tractable, given the analysis we did before, because three sort of line bullets here sort of make the state of the mechanism very simple. One is that I only accumulate agents from a single type. So if somebody declined a B, only people who decline are people who prefer an A. Because if you like a B and I offer you, you'll just take it and go away. So the people who I offered something to and are still in the system must all like A's. About the rest, I didn't ask them yet. And think of, again, of the waiting list as infinite. This is where it sort of buys us some tractability. The waiting list is still infinite and composed of agents whose type I don't know. So for the agents I didn't ask, I don't really need to worry about. The ones I did ask are all of the same type. And the number of those that accumulate is bounded, because we said once we get more than k alpha agents, the next agent will just take it. So the state of the system can be described as one of those numbers. Either I have some positive number indicating 1 to k alpha agents who declined an item and still there, that prefer an A item, they are alpha agents, or a negative number indicating there's some number of agents that declined an A item and are waiting for a B. And those are the states of the mechanism. And the transitions look something like this. So 0 means I didn't accumulate any agents who declined. 1 says there's one agent who declined a B and waiting for an A, and so on. Negative numbers are likewise people who declined an A and waiting for a B. And the transitions here are every period, every given period. So in a given period, I can at most get rid of one agent. So all the arrows towards the center is when I have, let me focus on this to make it clear. I have agents waiting for an A, and an A item arrived. So I had, let's say, 3 agents waiting for an A. 1 A arrived. I gave it to one of them. Now I have 2 agents waiting for an A. But suppose I have 1 agent waiting for an A and a B arrives. Now I have to search the waiting list for an agent who will take this B. In the process, I may accumulate many agents who decline this B and want an A. I may offer it to 3 different agents. All of them will decline the B and would want to join this buffer queue this set of accumulated agents to wait for an A. So that's why I have those jumps here. That I can have a lot of people declining an item and joining the supposed buffer queue to wait for the preferred item for this A. Yeah. And this is actually, you can simplify this Markov chain. You can break this down to a nicer Markov chain to work with. And then you can get the ergodic distribution from this, which is actually really easy once you break down the chain. And that allows us to get the probability of misallocation in this dynamic process. So the welfare loss will be 1 minus V. We generate V instead of 1 every time we mismatch an apartment. That happens with probability that I denote by C. And this probability in this model ends up being this expression, which has actually a pretty intuitive intuition. The numerator, 2p1 minus p, is the same expression that we got from random assignment. If we just give it to the next agent and we don't know what is type, we just randomly give him an item. The denominator is actually what makes this probability small, this probability of misallocation smaller, and that depends on the length of the two buffer queues. The buffer queues are how many agents we can accumulate waiting for an item, and the more agents we can accumulate waiting for an item, the less probable it is that I'll have to just randomly allocate it to the next agent. So if I have k alpha equal to 3, that means that whenever I have 3 or less agents that declined a B, the next agent who declines who I offer a B is guaranteed not to mismatch. Either he'll take the B because he likes it, or we'll decline it and go in the buffer queue. Only when I filled up this entire 3 spots and I go to the 4th, then I have a potential misallocation. This expression. And under this mechanism, I had no choice about designing the k alpha and k beta. They just came out of the incentive of agents. I solved sort of the equilibrium to get them. So graphically, the welfare loss looks like this. When V, the value of misallocating an item, is very close to 1, is very close to the value of getting your preferred item, it doesn't really matter whether you mismatch agents or not, so there's no welfare loss. As V goes down, welfare loss goes up, but you can see that there's discontinuities here. Discontinuities happen whenever the gap between your preferred item and less preferred item and mismatch item is enough to convince you to stay in another position. So here, nobody is willing to wait. Here, if you're first, you're willing to wait. Here, you're willing to wait if you're second, third, fourth, and 0 is not special in this model. You can have V's smaller than 0. Yeah? And whenever you can get another spot on this buffer queue, another agent who is willing to wait, then welfare losses will go down because the probability of misallocation goes down. And it turns out that those two things basically cancel each other out, and you get that welfare loss is something like C, like waiting a period. Yeah? Okay. So now the next stage, so this concludes like the analysis. We know what happens if you do a first come first serve. But given that there's welfare loss when we do this first come first serve, we want to ask, is there a better way? So let's, now that we understand something about the dynamics, let's try to design a different mechanism and a different policy for assignment to try to convince more people to avoid mismatching. And we can actually build up on the results that we did for the first come first serve, because what we use for calculating welfare is just how many people can we accumulate before the next agent will just take anything, this k alpha and k beta. And if I generate a different sort of policy of assignment, what happens after you decline an item, and I convince more agents to decline items, and I generate some way of convincing 5 agents instead of 3 to decline items, then I'll have lower probability of misallocation and therefore higher welfare. So now we'll think of this as a mechanism design question. In the previous analysis, I assumed that I have a mechanism, I solved for the equilibrium. Here, let's just assume that all agents will report their type, they will report it truthfully, but I must make it incentive compatible for them to report it truthfully, given what I will offer them after they decline an item. So what is the proper way to write those incentive compatibility constraints? Well, I'm going to ask agents either to take the item that I offer them, or to join a buffer queue. Decline an item, then you'll go in a buffer queue. If we go in this buffer queue, it means that you're going to entail some extra weight until you get your preferred item. And I'll have the constraint that this extra weight must be acceptable. So let's say I'm the third person who declines the B. That means that I'm joining the buffer queue in the third position to wait for an A. So I'm going to entail some expected weight, W3, until I get an A. Eventually I'll get the A, but until then I'm going to have some expected weight. This expected weight might be acceptable. I'm willing to tell you that I'm actually mismatch and go in this buffer queue if this expected weight is below this expression, the expected weight I'm willing to entail. If it's not, then I would lie to you. I would have an incentive to lie to you and say, oh, actually, this is my preferred apartment. This is my preferred item. So now I want to design a different kind of buffer queue, a different policy for the buffer queue, where the main constraint is that if an agent has to join this buffer queue, his expected weight must be short enough. And this actually translates this problem of matching of the efficient assignment to actually designing a buffer queue that can accumulate as many agents as possible. All of them must have an acceptable weight. So it's basically, if you're interested in queuing, this translates to a question in queuing theory, saying, how can I generate a queue which can accumulate as many agents and minimize the agents who prefer not to join the queue? Here, not joining the queue means I don't want to wait any longer for my preferred item. I'm just going to mismatch. Okay, so where can we do better? So we have this waiting times for the first come first served policy, and there's actually a lot of slack here, because the first and second agent under the first come first served policy are actually very happy to decline the B. There's a lot of extra waiting time they were willing to entail and still decline the B. And if I actually can increase their waiting time, and by that reduce the waiting time on 4 and 5, I may be able to convince 4 and 5 to decline items as well, and still make it acceptable for 1 and 2 to decline. And if that allows me to convince 4 and 5 to decline items as well, I have a longer buffer queue. More agents will be willing to decline items. Another way to think about it is that I give you a price. What is the price for getting your preferred item? So if you're the first in line, I tell you the price for getting an A instead of a B is 2 periods. But if you're 5, I give you a price of 10 periods to decline an item. But both agents should be seeing the same price. If we show different agents different prices, we get inefficiency. Here we would like to give all agents the same price, in a sense. Waiting time here, in a sense, serves as price. If we give all the agents the same price, we'll get a better allocation.
So this really is equivalent to the mechanism that I was suggesting before, where you don't tell people where they are, that they all face the same expected waiting time if they turn the item down.
So that's exactly what I'm going to do. Yeah. Okay. So how do we do this? So what I'll do is allow some randomization on the buffer queue. And the way I'll do this is I'll take a buffer queue policy. I say when you decline an item, you join a buffer queue. Its maximal size is k. To make it instance compatible, I must make some maximal size. And there's an assignment policy phi, which may be randomized. And when I get an item that is preferred by the people waiting in the buffer queue, I get people are waiting for an A, and an A arrives. I'm going to give it to somebody on the buffer queue, but which one depends on those probabilities phi. So if I set the phi for the first person out of k to 1, it means that I do a first come, first serve. I can also say that when there's k agents on the buffer queue, give it to the kth with probability 1. And that will be a last come, first serve. And I can also do randomizations. I can do a bunch of randomizations in between. And turns out those randomizations actually allow me to have this flexibility to balance the waiting time of different agents. So let me start by showing you how well can I do using this randomization. And there's obviously going to be a limit, because if I accumulate more agents on the buffer queue, in total, there's going to be more weight. So how much in total? So we can actually get the expected weight for random position in the buffer queue via a very simple expression. So if I look at a particular position and I have this complex randomization, the expected waiting time for a particular position is a pretty nasty expression and pretty hard to work with, and depends on this sphere, on the probability that I decide to generate, and it's pretty hard to say anything about general phis, but actually looking at the expected weight in the buffer queue gives me a very simple expression, and I can give you a one-slide proof. And this is using Glitter's law. Yeah, I'll talk about it in a minute. Given the expected weight for a random position, I can have an expected IC constraint. So if I'm willing to join every position in the buffer queue, if I tell you what my position in the buffer queue is, you must be willing to join it, then you also should be willing to join when I don't tell you. Because if all the options are acceptable, randomization over those choices must also be acceptable. And those end up being equivalent here. Actually, for now I should say that this gives me an upper bound on how many positions can I have in this buffer queue, given that the random one must be acceptable. Or this is like the bound that you sort of suggested of not telling me what my position is. So this gives me a bound. Let me just go through this Little's law, which, yes?
People are risk averse. It's better to not ensure that they wait for a longer period than
Yes, this is true. I'm assuming that all agents are risk neutral and only care about expected weight, but this is clearly a more realistic concern. So nice trick here is this pretty strong theorem from queuing theory, operations research. And basically, for some of you may know it already. For those who don't, it says that it's usually stated that the arrival rate times the expected time in the system is equal to the expected number of agents in the system. So the illustration is if you have a store and you have some inflow, some number of customers coming into the store, and some time that they spend, the expected number of customers you will find in the store is over the day is exactly equal to the arrival rate times the expected time they spend inside the store. And this is a law that works very generally. If we look at the system as the buffer queue, how many agents go into the buffer queue, how long do they spend there, we get that the total weight of all the agents together is just dependent on the arrival rates of agents and items. Balancing that out, that just depends on the size of the buffer queue. And then we get this expression. So it doesn't matter how we do the feed, the lotteries, we just redistribute the expected weight between different agents. In aggregate, the expected weight, the total expected weight that we have to allocate is constant. So given that the total expected weight is constant, all the expected weights must be below a threshold. We can't have any of them, we can't have the expectation of all of them together to be greater. Sorry, I misspoke. So given that all of them must be below the threshold, the expectation must also be below the threshold, and that implies that this k must be smaller than this expression, and given that it's also an integer, gives us a bit of a further restriction. So that gives us an upper bound on what we can hope to achieve, and actually it also tells us how we can achieve this, because if we have a bunch of expected weights, all of them must be below the threshold, and their sum is constant, then the optimal way is to distribute them equally. Because if any of them is strictly below the threshold, somebody must be strictly above. Or otherwise we have slack. So I'm going to denote this kind of new queuing policy, the load-independent expected weight. We're going to have a queuing policy that uses this randomization to generate exactly equal expected waiting time regardless of your position. So you come to this queue, and you're second in line, or you're eighth in line, or the queue is empty, your expected wait is exactly the same. So I don't need to tell you how many people are ahead of you because it doesn't matter. And this is sort of egalitarian or fair, not in an ex post sense. It may be that the randomization makes somebody behind me get the item before me, but it means that at the time when I come to choose between taking the item that is mismatched or the item that I prefer, we all face the same choice. We all face the same expected weight. So ex post, we may have concern of fairness, but at the time of choice, which is the critical time for incentives, I actually get the fairness there. Like I get the same choices for everybody. Yes?
Once people are in the queue, you know they're all one type. But if there's fewer people in the queue and you have to go to someone else, they can be of a different type. So does it bounce back into the queue if they refuse, or what do you do with the item?
So I always offer the item to the queue if I know that's the kind of item that the people in the queue like. So if I have a buffer queue of alphas that are waiting, I'm going to give them all the A's. And if I have a B, I will just try to offer it to new agents.
You said that even if the queue is empty, the expected waiting time is the same as if it was full?
Yes.
And so if the queue isn't empty but maybe has one person,
Yeah.
and you want him to have the same expected waiting time, and so you have to offer not to him but to some new person who hasn't queued?
So he was given the same expected weight when he chose to join the queue. Once he's on it, I know already his type, so I don't need to ask him again. He's sort of predetermined. He's just going to get the item according to the lotteries that the queue entails. I don't need to ask him again. Yes? Yeah?
So you said that the expected waiting time is constant. So when a person has been waiting for a period of time, but he still does not know his position, so his expected waiting time still that value, or
No.
is that
No. The expected waiting time at the time you join the queue is constant. After you join, your expected wait won't change.
or decline with time?
Yeah, so it actually may increase as well. I'll come up to an example, but I'll talk a bit about that. But the only promise that this mechanism gives you is at the time that you joined, your expected weight is acceptable. After that, it may be, your waiting time may change up or maybe change down. And to say why it will change up, think of doing a last in, first out, last come, first served policy. So in expectation, it may be that I joined the queue. In expectation, somebody may not join behind me. If nobody joins behind me, I get this immediately. If somebody joins behind me, I may have to wait a long time. In expectation, I have a short wait and I'm willing to join. After I joined and somebody joined behind me, I just sort of lost the bet in a sense. And then I may have a longer wait. And I'll talk about it in a bit. This is one of the problems of this mechanism, actually.
But
Yes?
in this case, if my expected waiting time increased, I probably would like to go out of this buffer queue and go to the ordinary queue, but I'm not allowed, right?
Yeah. Yeah, that's a restriction. And so if you think that once I told you that I prefer an A, then I don't have any incentive constraints about you. So I told you that I prefer a northern apartment. My preferences are pretty stable, so you're not worried about my preferences changing. From now on, you may be stuck waiting for a long time, and I'm fine with it.
You are fine, the person is not.
So overall welfare will be maximized. Some person will have to wait longer, but there are a lot of people who are waiting long on this system. Some people may never get assigned.
Yeah, but these people could take this possibility into account. Like,
So-
they could analyze that probably at some point I will be forced to do
So I agree. I'll talk like it is a problem with this mechanism, and I'll talk about it further. But if you take the incentive constraint as given, and you think this is the right incentive constraint, you may say, well, yes, agents may regret, but X until they'll make the correct calculation, say this is my expected wait, and I'm still willing to join. And you may be worried either that people will not be willing to take those bets, maybe they'll take them, like they won't calculate this bet correctly to take it, and you might also be concerned about the regret. Maybe public housing applicants have an emergency, and you want to make it incentive compatible for them to say, well, I changed my mind, now I want an A. You can't do this in this framework. Huh? So let me show you like a bit more about the randomization, and then it will actually show you that all those problems are serious problems of this mechanism. So the load-independent expected wait is this randomization, this randomized queuing policy that gets the expected weight for each one of the positions. So this, we said this is expected weight for a random position. If we make it for all positions, basically says all positions have the same expected weight. And this will be the optimal buffer queue policy because it achieves the bound that we shown before. And here, graphically, how it looks. So we said that there's a gap here and here, and we can eliminate the gap here and here. Little's law basically told us the total expected weight in the system is a constant. So those are expected weights based on different events. So it's not something that I can trade off just like shifting weight from one to another directly, but I can adjust the probabilities to adjust the expected weights, and it turns out that the total must sum to the same number. So increasing the weight of 2 by this amount allows me to decrease the weight of 4 by exactly the same amount. So this Liu policy gets me the optimal position, holding all the 5 agents exactly at the incentive constraint. All the agents are just indifferent from joining the waiting list or not joining joining the buffer queue or not joining the buffer queue. And not displayed here is that still, if I have a 6th agent, he's going to get mismatched. I didn't eliminate all of the mismatch in the system. I just got a buffer queue of size 5 instead of size 3. But I've shown I can't accommodate the 6 agents without increasing the waiting time for some agents. So there's no way to get 6. So this is what welfare looks like, just adding the Liu policy over the first come, first served. And if nobody is willing to wait, you can't really do anything once the mismatch item is actually bad enough so people are willing to wait for it. Then the Liu policy has many more discontinuities. Basically, it convinces many more people to join the buffer queue, roughly twice as much. Twice minus 1 is much. And that allows it to generate something like half the welfare loss. So now let me talk just in a minute of like now how I generate this randomization. So if I always give the item to the first agent that joined the buffer queue, I get the first come first served, and then the expected waiting times are going to be low for the agents who joined first and long for the agents who joined last. So if you're the first, you only have to wait for one arrival, the second has to wait for 2 arrivals, the kth will have to wait for k arrivals. If I always give it to the agent who came last, then you can show, like it's pretty intuitive, that if you joined last, nobody is allowed to join behind you. You must be getting the first item, the first A that will come along. So expected waiting time is 1. And you can show using Little's law and in just induction that it's actually the expected wait for each one of the positions is exactly the flip of this. Well, there's now to calculate this, you have to take into the fact that there's some sort of gamble the first agent is taking. If I'm joining and I'm the only one, there's some chance that I'll get the next item if nobody joins behind me. But there's some probability that people will join behind me, and if k agents join, I have to wait more than k arrivals, because before those k items will arrive, maybe some other agents will join as well. So, like there's 8 people now, and then some items will arrive, will be down to 5, and then we'll go to 6, and then some items will arrive, and we'll go down to 4, and then some items, and so on. But I have to wait until everything clears out. Some agents will join in the middle. So my waiting time, if the buffer queue condition on the buffer queue getting full when it's last come first served, and I'm in the first position, is actually really, really long. But you also get some probability of getting it without anybody joining behind you. And on expectation, it turns out to be exactly k. Yes?
Yeah, but the scenario you just described, the one where I was supposed to be waiting for 5 people, then 6, 7, etc. I thought when I thought about implementing this policy, I thought that we first collect a buffer of certain size that you, and then you only give to people from this buffer the respective apartments, and then you collect another buffer. This is not the way you...
So I only give apartments that are matching to those people. So if I have alphas waiting, people waiting for an A, I give them all my A's.
Yes, so
But if I have a B, I still offer it to other agents, and I want to...
wouldn't you have 2 buffers, two full buffers, start with let's say you full your 2 buffers, then you give only A to the buffer A, B to the buffer B, until a buffer, until all the people in the buffer get the buffer, and then you just start a new buffer, no?
So the buffer is the mismatch that I accumulated. So whenever I have a B, then I have to tell those people, no, you should wait a bit until I get the A. So the like I always have some buffer, either for A or B, for the mismatch.
But not
I never have both. I never have both at the same time. Huh? If I have somebody that I know that wants a B, I just give them the B and that's it. Like I just finished the period.
Okay, so the
Yeah?
implementation still gives the logic from before that you don't want...
Yes. It's just, it's the same logic from before, just like what happens when you go on the buffer. Now, instead of just giving to the people in the buffer according to the time that they were joined, now we do a randomization that tries to balance the expected weight of different agents.
But you could have implemented it in a way that you have 2 buffers, that you start from the list, you just fill buffer A, buffer B, and then you give only to the people in the buffer.
I could. I would need some other framework to analyze what will be the incentives and welfare there. And my guess is, as far as I could see, it doesn't help you. No? Okay. Okay, so we talked a bit about the lottery here, but the useful thing about it is that this lottery actually gives too long of a weight to the first agents and too short of a weight to the last agents. This is actually exactly the opposite. So what I want to do is just find something in the middle. If I find something in the middle, everybody will have the same weight. So I go through this procedure, and like it's just some calculation.
You just randomize which comes out.
So I can't just, because I need to continuously, I need to commit to the policy when you join in.
You're told when you join that you will either be first come or last come with 50-50 probability, and after you decide, you get the randomization is.
But what happens if so I have to think about it. I'm not sure, because then it depends what happens to the next guy after you. And if the next guy after you with 50% chance will go ahead of you, with 50% chance will go behind you. So I'm not sure it actually will actually give you a waiting time that is equal to the average. Because if you were the only person and you could randomize this, it would work. But there's some interaction with the other randomization for the other people, because you can't do those randomizations independently of each other. Because I trade off your priority against other people. But I'm actually not sure about the exact calculation, but I'll be happy to talk to you offline. Yeah. Okay. So those probabilities end up generating this Liu buffer queue, and what is actually happening is that it's something like a mix between a first in, first out, and last in, first out. So when more agents join, so if there's only one agent, he gets it. If the second agent joins, he gets it with some probability, and the first agent gets it with some probability. If the third agent joins, then the first agent will get it with 0 probability, and they shift probability towards the last agents. But they don't shift all the probability completely. It's not that the last agent gets it with 100% chance. It's some sort of like milder shift. And that ends up generating expected weights that are exactly equal between the two, because when other people join behind you, I'm not going to put them behind you. I'm going to sort of randomize and give them priority over you just enough to make them have the same expected weight as you did. And one is in pretty poor position when 3 people joined, but he's pretty good when he started, because he had some probability of getting it without any people joining behind him. So in expectation, he has the same expected weight, but like people were concerned here, he is taking a lottery, a gamble of whether people will join behind him or not. So yeah, so I told you I'm concerned about this too, and yes. So there's a couple of ways to express this concern. One is that, agents' belief matters. So if I think that agents will join behind me, I'm risk averse, or I'm just pessimistic, I won't be willing to join this buffer queue. And this is also very connected to the fact that I may have regret ex post for joining. And a second concern is that the probabilities for this randomization require me to know something about the system. I need to know those p's. And to calculate that, I want to have a buffer queue of size k, of k equal 3 here, I need to know that 3 is the right number, that people are willing to wait. The expected waiting time that I can allot to them will create a buffer queue of size 3. But if I got it wrong and it's actually a size 5, I'm still forcing them to mismatch after I accumulate 3 in this policy. And I can't just adjust to size 5. Size 5 will have a different randomization. And actually, I didn't find a way to generate those probabilities in a way that will be scalable, that will generate the same probabilities for different size mechanisms. And in any case, there's a lot of dependency on parameters that we're not actually that sure that we know in practical environments. So this P is known in the model. In real life, I wouldn't necessarily know what the right P to use is.
But the agents do know the P, because they have to be able to calculate that they're indifferent.
It's that's another concern, because if you're a public agent applicant, you probably have some information on how frequent apartments in the north are versus apartments in the south.
You're
But-
assuming the agent knows at least as much as the mechanism design.
Yeah. And I think all of those are real concerns when you think of implementing something like this in practice. As well as the fact that this is complicated in a way. So now that we finished describing the optimal mechanism, I'm going to move to the third part and ask for what I'd call a robust mechanism. Robust is used in a non-technical sense here. Right, so I'm not talking about robust mechanism design, although I'm thinking of a similar kind of ideas. I want to generate a policy here using the same kind of tools and the same kind of intuition, but have 2 points that this previous mechanism missed on. One is that I want it to be safe for agents. I don't want the agents to need to do sophisticated calculations or have ex post regret. And this, I think, in examples like public housing is important because you don't expect the agents to have correct beliefs all the time. And one of the reasons I want to give the agents as much information as possible is because I don't want them to decline or accept based on being misinformed. And since I think it's a real concern that agents will be misinformed, let's lower the dependency on the information here. Like putting everybody exactly on the incentive constraint may not be a great idea if you don't know what is the incentive constraint exactly is according to their beliefs. And second, that I want something that's simple for me. So a second price auction is actually really nice in the sense that it doesn't depend on the parameters of the problem. You don't need to know anything about to say second price auction will get you efficiency. Getting the reserve price is a bit harder. You need to know what is the distribution of values, of valuations there. So I want something that is more like this general rule that will not necessitate me to know too much about the environment to get a mechanism that works well. So let's start from the simple. So first I'm going to ask that I have a mechanism that works not just for one size of buffer queue, but for all sizes. So instead of having this very general form of randomization that I had before, I'm going to ask for a simpler form. Give a weight to each agent, and the probability that the agent gets the item is just his relative weight out of all the agents that joined. So that would generate me probabilities that are sort of consistent between different sizes of the queue for any size of the queue. And I can still generate the first come, first served here by giving a weight 1 to the first agent and 0 to all the rest. I can still generate the last come, first served by having those weights increase vastly from one to another, or approximately the last come, first served by having vi plus 1 greatly bigger than all the v's before him. Oh, actually, I didn't restrict that those have to be real numbers, so let's just have them ordinals. No fans of ordinal jokes? Okay. Okay, so this gives me that the mechanism is scalable and generic, and I would like that actually don't tailor the mechanism to a specific environment. One thing that will be helpful in forming the definitions and notation that I may still find it useful to restrict the maximum number of agents to the queue. And I will actually find that for the optimal mechanisms they need, this is redundant. I will allow the mechanisms to do this, but for the optimal mechanism I find, it will actually turn out to be not necessary to do so, with a slight loss in the strategic properties of the mechanism. So think of this mechanism. I have this scalable mechanism. I can decide what is the maximal size of the mechanism. And now I have my incentive compatibility constraints, whether the size and the randomization that I decided on actually makes it incentive compatible for agents to join up to this size of the buffer queue. And now I'm going to ask not that it's incentive compatible under the true beliefs, under the true dynamics of the system, but I allow agents to have arbitrary beliefs on the types of agents that join behind them. So I want to say, I think that everybody behind me also wants an A, so I'm not going to join a last come first served buffer queue for A's, because I believe that everybody behind me will want an A. So that's something that I'll denote this belief by sigma, and I'll ask something bigger, that under any belief on the types behind you, you'll be still willing to join, which is your expected weight will still be acceptable even under this more general and not necessarily true belief. And this is nice in two ways. One, it requires that the optimal response of agents is not just Bayes-Nash equilibria. I'm actually asking here for it to be a dominant strategy to join the buffer queue. And we like dominant strategy. It makes things easier for agents. And second, that this is exactly equivalent to being a no regret, to have no regret, that you never joined the buffer queue, and then once other people joined, you now regret that you joined, because it's actually very simple. If I think there's some situation that I'll have regret, I can just tailor my belief to lead exactly to that situation. So I'm basically asking now more of this mechanism, and this is actually nice because then I'll get some mechanism in which I can also ask people to leave the buffer queue once they're on it, because I know that it's in their best interest to keep on waiting unless something really changed.
No regret constraint is a
Pretty strict one. Yeah.
People understand lotteries. They accept them all the time when they buy insurance. Basically you're saying that you don't want people to feel regretful for having taken a lottery.
Yeah.
Which is
it's a strong constraint.
It's a strong requirement.
Yeah. But it is satisfied by the first policy that we talked about in the first come first served. When you join your buffer queue, your situation does not depend on whoever joins behind you, and you can and as time goes along, you can only get a lower and lower expected weight. So there are mechanisms that get this, and I'm going to ask something that generates this, but still gets closer to the optimal. And now this slide kind of looks horrible, but it's actually or maybe it doesn't look horrible. Anyway, like now, I need also to tell you what I mean now by a better mechanism, given that I don't want to commit to specific parameters of the environment. So how can I compare two mechanisms for overall performance for different parameters? So let's denote by this k phi of w bar the maximal size I can of the buffer queue I can achieve for willingness to wait w bar, if this is the acceptable weight of agents. And yeah, this is a typo. Okay? This should be cape C here. So now I want to compare two mechanisms, and the natural thing is to say that one mechanism is known to the other if it can achieve the longer buffer queue. Lower buffer queue again is like lower percent of mismatch. So if it can achieve a bigger buffer queue for any parameter. So this, of course, will not bias much because the previous result tells us you want to use different mechanisms for different parameter values. So there is some trade-off there. You can't be good for everything at the same time. But I'm going to use something else for the equation, that I know that the mismatch probability looks like 1 over the buffer queue size. So 1 over k. So intuitively, if I have a buffer queue of 20 people, I can accumulate 20 people. It's less important to accumulate the 21st, because I'm less likely to use the 21st. But if I have a buffer queue of 3 people, getting the 4th is actually very important, because I'm very likely to need the 4th. much more than I am to need the 21st. So I'm adding a criteria saying that I want to do as well as the other buffer queue, or to achieve at least a minimal size. And this will be my criteria for getting a good policy. Either you do as well as you can, or at least you do a sort of like a minimal threshold. And this basically means I want to optimize the policy so I get the second person to wait for as little acceptable weight as I can. The third, as little conditional on getting the second to wait. Now, when people are a bit more patient, I want the third to wait for as minimal weight required as possible, and so on. So, I think this is a useful way to compare the different mechanisms. I think it's sensible, and it also sort of tells us sort of how to optimize. And this mechanism will turn out to be the optimal mechanism, but it's actually very simple. So it's a queuing policy that in queuing theory is called zero, service in random order. And basically what it means is that the buffer queue is not a buffer queue, it's not ordered, it just gives everybody the same probability. So in the Liu mechanism, I said everybody should have ex ante the same expected weight. Ex post, they may be in very different situations. This mechanism is doing the opposite. Ex post, everybody in the same position. So if an item arrives, there's an equal probability for every agent in the buffer queue to get this. And basically what I offer you when you join the buffer queue is that you'll join a pool of people with priority. Collectively, you're going to get all the A's before anybody else. Which one of you, it's just equal probabilities. And this actually ends up to be the optimal mechanism. This is very simple, a very simple randomization. But it turns out to be the unique and dominated mechanism. And the intuition for this is that I want to get an extra agent on the waiting list as soon as I can. I want to incentivize the K+1, the last agent to join. This is the hardest person to convince to join at the first come, first served. Like he's essentially behind all the previous people. I want to lower his waiting time. So how do I lower his waiting time? I give him higher priority. But the more priority I give him, the less priority I give other people. When do I have to stop? When I can't make him better off than the other people, because then I may make them regret joining. When I make them regret joining, I lose a bunch of the properties that I talked about. It's not safe for agents. Now you have to do those lotteries. So what I want to do is make them equal. And there's a bit of mathematics to show, it's actually because it's a dynamic policy, like you have to be a bit careful of not confusing the ex post probabilities with the ex ante, but it works out. And you get that treating everybody as the same ex post actually sort of gives you this undominated mechanism, because it's the most incentives you can give the last person to join without risking any of the previous ones. And how does it do? Well, it's of course not the optimal mechanism. So if I try to get 5 people on this serial buffer queue, I get that the last position have an unacceptable waiting time. They won't actually join. But I do get 4 people on this buffer queue. So you can see that I would like this line to be completely flat. If it was completely flat, I would get the optimal mechanism. So it's not completely flat, but it's flatter than the first come, first served. It's still better to join with equal probability, having equal probability to the previous agents, rather than having, rather than in the first come, first served being behind everybody. But that actually creates also some extra waiting time for the first agent, because now the first agent has some probability of just getting the item without anybody else joining. With some probability, other people will join behind him. And then he'll have to wait maybe longer. He's still better off, because it's still better to join a zero buffer queue which is empty, because if there are 4 people on it, I have to split my probability with them. If I'm all alone there, then I will have some probability of getting this before anybody else joins. But even if other people join, actually I'm not at risk, because the last person was willing to join. I'm in the same position as he is. So I will never have regrets, because if the last person was willing to join, I'm willing to stay. So this is actually a nice property, and this actually also means that I don't need to decide on this K. I can just say this is a zero buffer queue, join if you wish, and in equilibrium, I'll get the right maximal size, assuming that everybody has the same cost of waiting.
Assuming that people know what P is.
Yes. Yeah.
So the mechanism designer doesn't have to know P, but the agents.
The agents, yeah. Or at least they all have to agree on this P. As long as they agree, I'm fine. Yeah, and don't come complaining afterwards when we learn something different. Okay. Okay, and here's a comparison of welfare. How does the zero does in terms of the same graph that I showed you before with welfare loss. Again, this is for specific parameters, but we can see again, we get the same trend. As V goes down, more agents are willing to wait. We get those discontinuities. The zero mechanism will convince more agents to wait than the first come, first served. So it breaks more often than this one, but not as often as the optimal one. But one big thing for the zero mechanism that is not displayed here is that every time the line breaks for the liu, for the optimal mechanism, we need to completely redesign it. The zero is actually the same policy. I just state the policy and I don't need to redesign it or know anything about the environment to implement this. And I think it compares rather favorably. It gets more than half of the gains from moving to the optimal mechanism. And it has a bunch of other nice properties. I think I'm out of time, but so it was said that we don't need to restrict joining. I don't need to decide on the maximal size K. I can just have it be set by the equilibrium of agents. It's simple and it's regret-free. So if I'm concerned about agents having an emergency, I can just let them tell me that they have an emergency and say that they changed their mind, because I know it's incentive compatible. They wouldn't want to lie to me, because staying in the buffer queue is incentive compatible as well. Not just joining it, but staying is incentive compatible. And yeah, and so let me just conclude, given that I'm out of time. So we started by thinking of assignments in waiting lists, and maybe getting back to sort of Eyal's question. Like the issues in a waiting list are very different from in a queue. You have to think about how to offer things to agents over time in a way that will make them decline items. You do want them to decline items. That's something that is against the policies that you often see, that people are not allowed to decline. Often in public housing, like if you see an apartment, you have to take it. It's actually, I think it's a very misguided policy, because it sounds bad when you decline an apartment, but what you're essentially doing is saying, I'm willing to wait longer, let somebody else have it. And given that the system is overloaded, there's a lot of people who want this. This is actually something that you want to encourage, not discourage. And when we want to analyze the, sorry?
So here, the heterogeneity comes from different tastes.
Mm-hmm.
But you could imagine heterogeneity where some apartments are good and some apartments are bad.
Yeah.
And in that case, you wouldn't want some. Everyone agrees that this apartment is better. If people have the same tastes, you might not want people to decline apartments.
So if you have a vertical differentiation and some apartments are just worse, then I expect that people who will take this apartment are the ones that have a long expected wait. Some people will wait a lot for the good apartments. Some people will not be as willing to wait and take the worse apartments. But as long as all the apartments end up being assigned, as long as when I reject and decline an apartment, it will go to somebody else eventually, I can still facilitate a better assignment by saying even somebody else has a lower cost of waiting. He should get it and not mine. Oh, sorry, if somebody has a higher cost of waiting, he should get it and not me. And I still want to encourage somebody to decline. And the idea that there's a positive externality by declining, since when I decline, my waiting cost will go up, aggregate waiting costs will stay the same, then I would be more impatient than society would want me. I don't, even in this case, I don't see why you should worry about somebody being less impatient than society wants him to be. Since I have a positive externality on other people when they decline, I think that you always will be concerned that people are not as patient as society would want them to be.
Well, I had in mind a case where people are homogeneous, and I might think that by declining now next period I get better apartments. I'm deviating from the.
So I think one way to justify this is
that might justify the
Oh.
policy to prevent people from deviating in that way and getting a better apartment.
okay. I think that in general you'll be worried about people being too impatient and taking things too early rather than taking things too late. One exception to that is if there's some bureaucratic cost that they don't see when I decline. That's maybe something that I should be concerned about. But I think that's smaller issues as far as I can tell. And people should be allowed to decline generally more. Yeah? Okay, so on the technical side, then it's a dynamic system, but you can actually get a very tractable analysis by just thinking not of the full waiting list, just think of the people who declined offers. That gives you this buffer queue representation and a pretty tractable Markovian representation. And sorry. Yeah, I'm allergic to some Markov chains. I had. Okay, so for the very stylized model that I had, you get a closed form solution, and actually you lose the closed form pretty easily once you try to add more things to the model, or at least it makes it much less nice. But you can simulate it, even if you try to add heterogeneous waiting cost or more preferences, more items. It's still very simple things to simulate. So you lose closed form, but it's actually pretty easy to make it realistic and simulate. And in terms of policy, then I think that the optimal mechanism for the reasons that you raised as well is not a recommendation that I would suggest to public housing authorities or anything like that. But I think that the intuition that it generates and manifests itself also in the zero buffer queue give more probabilities to the last agent, because we want to equalize expected waiting time at the time that you decide. The zero mechanism achieves this in a pretty nice way. It's a pretty simple mechanism. It balances the waiting time over different agents, and I think it's actually a good policy recommendation, which may help reduce inefficiencies. So yeah, so I think it's nice, and if you have any comments, I'll be happy to hear, and thank you very much.